Today's topic is history of atomic structure. So, what this world is made out of has been a big bothering question to the scientists and philosophers. It was only about 2,400 years ago when the people started to answer this question. So the first one to answer this question was Democritus, the Greek philosopher from 400 BC. He first coined the word atomus, which came from A means not, and tomos means divisible. So when these two parts are merged, it means that indivisible. So what he wanted to say by atom is an indivisible particle. Indivisible particle. What Democritus believed was that if we keep on breaking down a matter, we're going to end up with a particle that is eventually unbreakable or indivisible. That is a basic idea, but quite clear and straightforward, that first attempted to answer what this world is actually made out of. And the next one to attempt to answer this question was Aristotle. Aristotle first came up with a four-element theory, and he believed that this world is made out of fire, water, air, and earth, soil. So these four. But the problem with this model was that now we know that water is dihydrogen monoxide, water, H2O. Earth and soils are made out of minerals and decomposing materials. And air is composed of nitrogen gas, carbon dioxide, oxygen, and those chemical compounds as well. Fire is just a chemical reaction, specifically combustion. So these four-element theory seems quite erroneous, but the old people just believed it because it's Aristotle who said it. You know, he was so famous, and what he said was always believed to be correct. Anyway, it took 2,000 more years to figure out the next part of this process. John Dalton, an English scientist, was the first one to suggest a modern theory of atomic structure, and he came up with a model just like billiard ball. Just a spherical, small particle that is indivisible, that's forming everything in this world. So his postulates were like this. He said at first, atom is indivisible. Second, compounds are always made in a fixed ratio of atoms. And he also said the same type of atoms, like oxygen to oxygen and carbon to carbon, always have the same property. And he also said that different types of atoms, just like gold to silver and silver to gold, have different properties. However, even though these theories seem to be much better than Aristotle's, he said his postulates had some errors. First, atom is not indivisible. There can be electrons, protons, and neutrons, which we are going to talk about later on. And the compounds don't always form in fixed ratio. You can know this when you look at the organic compounds. And same types of atoms always have the same properties. I can't really say that because there are some isotopes. There can be carbon 12, carbon 13, carbon 14 with different number of neutrons and different atomic mass. In case of the different types of atoms always have different properties, this fourth postulate is not always correct, because some elements like calcium and argon have the same atomic mass, but they're not the same element. So even though John Dalton tried to suggest a model that can explain the basic components of this world, even his model was not really accurate. So the next one to try to explain this was J.J. Thomson from 1904. He discovered a negatively charged particle during his cathode ray discharge experiment. A cathode ray is a ray that flows from negative charge to the positive charge, and he was able to identify that the cathode ray bends to the positive side when he put an electric charge. Also, he could observe a shadow when he put an object in front of the cathode ray. And he also observed that the cathode ray bends down to the S pole when he put a magnetic field on the discharge tube. He also found out that when he put a fan in front of the cathode ray, it rotates. So he could define this cathode ray as first negatively charged, Second, affected by a magnetic field, is special to the S, and it's going straight, just like light, because it forms shadow. And the last was that it's a particle. It should have a mass to make the fan to rotate. So he defined this particle as an electron, which is usually abbreviated as E minus. And he also came up with a model, plum pudding model, to explain the structure of atom. And what he suggested, or what he theorized, was like this: there's an atom which is overly positive charged, because he had to make the particle into neutral, because he knew that the atoms are not charged in terms of electrical charge, and he put several electrons to balance that, and he called this a plum pudding model. Even though his model seemed to be quite reasonable, his model couldn't explain everything because of this experiment by Rutherford. Rutherford's gold foil experiment in 1911 was like this. He put a gold foil at the center of this apparatus, and he surrounded it with the alpha particle detector, which is positively charged. And then he bombarded the gold foil with the alpha particle. What he already knew is that the atoms already have positive and negatives. And since there are negative particles inside it, alpha particle, a positively charged particle, is supposed to be diffracted, just like what these lines are showing. This one, this one, and this one, and this one. Some alpha particles were actually reflected, not refracted, by the gold foil. So what he theorized was that there is actually a positively charged particle at the center of the atom. So that positively charged particle is bouncing back the alpha particles. And he came up with another model with the positive particle at the center and the electrons surrounding the positive particle. And he called this the center particle as a nucleus made out of protons. So this is called the Rutherford model, which could explain what Thomson's model couldn't explain. However, it couldn't explain another phenomenon, which Niels Bohr will explain for us. Niels Bohr, a Danish scientist, came up with a planetary model of atomic structure. The special thing about this model is discrete energy levels. What the scientists could observe back then was, like, when you put energy into an atom, hydrogen especially, electron emits energy or light. And depending on the amount of energy, the light emitted was quite discrete. That meaning that there must be a discrete level of energy. And what Niels Bohr suggested is there is an orbit the electron is rotating around. And as they get energy, they jump up to the next level and they go back. As they go back to their own state or ground state, or lower, more stable state of energy level, they emit energy as they get stabilized. Well, his model worked very well, only for the hydrogen. He couldn't really accurately predict what the light and energy and the electrons would behave in atoms or elements other than hydrogen. But anyway, he could explain it quite well, so he was awarded a Nobel Prize. Anyway, what Bohr's model couldn't really explain very well was improved by Heisenberg, Schrödinger, and Chadwick. Heisenberg was the first one because he came up with an uncertainty principle, which said that when you know the exact location of the electron, we can't really know the exact momentum that electron possesses. And when you know the exact momentum possessed by the electron, we can't really know the position of that electron. So that's very uncertain. And the next one, Schrödinger, said was that, well, if you can't really certain where the electron is, how about showing it in form of a wave function? That's a Schrödinger's equation. And as Heisenberg and Schrödinger attempted to explain the behavior of electron, that later on developed into an idea of orbital. And in case of Chadwick was the one to propose the existence of neutron, which is proven to be correct. And before, people only thought of electron, proton, these two to be the basic components of the atom. But as Chadwick Chadwick added neutron, he could perfectly explain the atomic mass of the elements. So, as Heisenberg, Schrödinger, Chadwick, Bohr, and the other previous scientists try to explain what this world is working like, we currently have a model that's quite reasonable, but still our model is not. It's still not a perfect model. And also, since the current modern atomic model is pretty hard to draw, we still use a planetary model suggested by Bohr because it's quite straightforward and easy to recognize. And yeah.